In these next few videos, we're going to look at calculating a titration curve involving a weak acid or base as our analyte. Again, we will always have a strong acid or base as our titrant because we want this reaction to go to completion and to be heavily favoring the products. So we're going to look at an example here. We'll have a weak acid as our analyte, and we'll do an example that's in your textbook. And the weak acid we'll look at is MES. I can't even remember what this stands for, but this is the structure. I have N plus here. Then we have CH2, CH2, SO3 minus. Okay, so this is our weak acid, MES, and it has a pKa, which we will need for calculating all our points on the curve, of 6.27. And this is going to react with hydroxide. We'll use sodium hydroxide as our titrant to form the deprotonated version. So the proton gets lost from the amino group. So we'll form O, N, without the H plus, CH2, CH2, SO3 minus, plus water. All right, so this will have a large K value. It's 1 over KB, which is going to be something like 5 times 10 to the 7th. So this is a very, very much favors the products, and so this is what we want for a titration reaction. And this is generally going to be true for a strong acid or base plus a weak acid or base. All right, and so what we want to look at here is, what's going to happen in terms of the titration curve. So let's imagine a specific case here, so that we have our initial solution of our analyte is we'll do the same volumes that we were looking at last time. 50 milliliters of 0.02 molar solution of MES. And we will titrate with 0.1 molar sodium hydroxide. Okay, so since the volumes and concentrations are the same, the equivalence point is going to be the same. So the equivalence point will still equal 10 milliliters, and you can look at the previous videos to go through that calculation. It'll look exactly the same though. Our moles of acid, we have 1 millimole of acid, so we'll need 10 milliliters to get 1 millimole of our sodium hydroxide to react with all of that acid. Okay, so then we can think about what's the pH at different points along this titration curve. So we'll consider at the beginning of the titration, before the equivalence point, at the equivalence point, and after the equivalence point. So 4 different places. We'll do the before the equivalence point in this, or before the titration even starts in this video. So if we're looking at before titrant is added, we just have a weak base in solution. And we know how to find the pH of that. We'll use the Kb value. We know that Kb will equal x squared over the concentration, which in this case is 0.02 minus x. All right, so this is a situation we've seen before already. Okay, so sorry, Ka. This is a weak acid, not a weak base. All right, and so we can go ahead and solve this for x. I won't go through all the details of this, but x is going to be equal to the concentration of H plus, which is equal to 1.03 times 10 to the minus 4. And that gives a pH very close to 4, pH of 3.99. Right, so nothing special here. This is a weak acid, not base. A weak acid in solution, and so we would solve this like any other weak acid problem. So then once we start adding titrant, we'll look at that in the next video and see how we find the pH and what's going on there.